a related question. So when would you say it's appropriate to avoid SEO containers or smart pointers for performance reasons? Like, can you think of a couple of cases where it may be necessary?
Okay, so I tried to address that question in the book at some point. So suppose you have to think about why you're using something. Okay, so let's take vector. It's an interesting use case. We all tell people use vector by default. It's fast, it's efficient, and it's safe for the most part. And effectively, it's a great tool. If you're using a vector, you want an array that dynamically grows. When you add stuff to it, there's not enough room. Awesome. I think all modern languages have something like that, and ours is blazingly fast. But of course, there's costs to everything. If you're using a vector and you want it to be efficient, it has to be bigger in size than what you really need. Because the point is you allocate more memory such that when you add stuff at the end, the memory is already there and you don't have to reallocate. That's why it's quick. It's using more memory. And when you add stuff to a full one, at that very moment, you have to reallocate, and that addition will cost you something. So if you see it coming, you can maybe reserve the memory ahead of time so that you don't pay it when it's critical. So we discussed that. If you want a fixed size array of a size at compile time, but that's reasonable, not too big, just use an array. It's totally fine. If it doesn't have to grow, why pay for the vector? Because vector, it needs to know the capacity, the number of elements, and where it starts. So there's like three bits of information. If you have an array of fixed size, just knowing where it starts is sufficient because the rest is a constant, so it's easy. When you're in the middle, there's a thing in the standard for something that you need to allocate dynamically, and because maybe it's big or you just know the size at runtime, but it won't grow. But you can achieve that with a unique pointer of array. So you allocate your array and you give it to unique pointer, but then you have to take the size into account separately because the unique pointer knows how to destroy your object at the end, but doesn't know how big it is. But you can write an in-between container, do that too. You can have a fixed size array. So if you have where it starts, what the size is, because you want to remember it, but you don't need it to grow, well, maybe vector is too much for you. So sometimes you want to save space and you want to save features you don't need really. Of course, if you use a vector and you never grow it, you're not going to be using the features anyway. But the point is you can get something that is leaner. So if you need less memory footprint or smaller objects or whatever, by rethinking your approach to the problem. Do I need to grow? No. Well, maybe it's not vector I need something more custom, something like that. So yes, this is one example of a case where then smart pointers are cool, but they define responsibility over a resource. When you just want to use something, you don't need a smart pointer. Just a raw pointer is enough. As long as you have this system array, you know how big it is. So, and you won't get that just from me. You get that from many other committee members, I think. Once you have, let's say, a unique pointer in your hand, there's nothing wrong about passing the raw pointer underneath to your different functions, as long as the moral contract that everyone has is if it's a raw pointer, you're not the owner. You just use it. The owner is the smart pointer. That's why it's there. So yes, you don't need any overhead. Even if it's just debugging overhead, you're debugging your stuff. If it's a smart pointer, you might go through the smart pointer member functions because your debugger will get you through that. Then it will slow you down as a human. There's a cost to that too. But if it's a raw pointer, it's very like you're directly on the memory, you just use it. It's not slower at runtime, but your debugging experience might be nicer. So yeah, so there's ways or reasons or moments when you need those fancy tools. And sometimes, well, when the responsibility issue is done with, you know who's responsible, it's clear in your code. Raw pointers are awesome. And they're fast, they're easy to copy, easy to move. Awesome.
And is that what comprises manual memory handling? Because that's what my next question was about. It was about what criteria justify switching to manual memory handling.
Well, the whole point of the book is not to do that, but there's always cases. If you have to resort to manual memory management, what you will usually do is try to encapsulate that thing in such a way that you won't get in trouble. If you allocate something, you give the ownership to some object, and you try to make sure that with its lifetime comes the control over the moment where the resource will go away. So smart pointers do that. Vectors do that. Your containers will do that in general. When do you go for manual memory management? So when is it accurate to do that? So in the book, what we're trying to discuss is you try to avoid doing manual memory management if you can. So you inform objects that have clear lifetime boundaries of their responsibility towards the stuff. So smart pointers define who's responsible for resource. Containers do that too, so on and so forth. That makes everyone's life simpler because you know who will get rid of the resource at the end, or at least you know what the rules are in the case of shared pointer. Now, sometimes you have exotic cases. You really want to use exotic memory. So you have a black box in a race car or in a boat or in a plane, and you have a non-volatile memory there that you really want to use. Well, you might want to get your hands dirty a bit and see how to use C++ in ways that let you use that exotic memory in your code. So we have a chapter on that, of course, because that's useful. Or share memory in the computer so that two processes can communicate together. I've done a lot of projects that use that in the past myself. If you're going at a lower level, so say you're writing a game and you have a scene where you know what the rules will be. You know how many objects of this type will exist at worst. And you kind of know the pattern in which the game will go. So you can predict some things about who will need resources, in what order they will be freed and allocated, depending what you're doing. When you know these little things, sometimes you can be faster, more efficient, more predictable than standard tools that are more broad in general. So again, we get there in the book because I think it's an important topic. When you know what's going to happen, or when at least you know the context, you can always beat the system. The system is very, very good on average. It's very good for the common case. It's very good in general. Your standard libraries will provide very good facilities for manual memory management, very efficient on average, but they don't know what your problem is, and you do. So when you know the rules, you can do better. We actually have a chapter where we do blazingly fast stuff because we know things, and we show that. I think it's a fun chapter. People, my technical reviewers like this one because being someone who played Dungeons and Dragons and likes Lord of the Rings and stuff, we kill orcs. That's so people like monsters will probably smile at this one. But yes, so sometimes when you understand the context, well, you can by going a bit lower and taking control over things, you can be faster. So, but these low-level features, you will still try to encapsulate them if you can to avoid humans having to manually take something here and bringing back there. Okay, because they get in trouble when they do that. So the point, I'm going to quote, I hope correctly, Scott Myers here, who's well known in the community, who's retired now, as far as I know. You cannot prevent people from doing stupid things. So you need control to your users. I mean, they sometimes they need to do stuff and they need control over the little bits, but you have to make sure that the easy thing to write is the correct one. So we provide them with tools that alleviate their tasks from the bad stuff and the dangerous stuff. If they don't need to do it, that's very efficient. And you still give them control over the little stuff when that's what they need. I don't know if that's a correct answer to your question, but I really tried.
No, it is. It is. And thank you for that. And we're going to wrap up this section of the interview by talking about, I want to ask you about tools like Address Sanitizer or Valgrind in detecting memory issues. How useful do you think such tools are?
They're awesome, but I'm going to be a bad guy. I don't use them much, but they really are very good tools. Of course, there's costs to everything, but the sanitizers are very good tools. I think everyone should use them once in a while just to make sure they didn't make a mistake recently. It should be part of everyone's test processes. because sometimes you're convinced you do something right and you realize you did something wrong. In the same sense that you should try to raise your warning levels when you compile. If you're using Visual Studio, try W4, something like that, or maybe not WR with GCC because it's too noisy, or Clang, but raise your warning levels a bit just to make sure that by default they don't necessarily tell you as much as they should. And then if you're doing that, sometimes you discover stuff about your code. So I'm lucky, I'm very experienced. Even when I raise the warning levels, I don't get much noise, to be honest. But I think every team should try these. So try your sanitizers, see what they tell you. It probably won't cost you much. Maybe it won't even cost you anything if there's compile time stuff instead of runtime stuff being done. But it will make you feel more comfortable with what you did, and that's already something.